One-to-one and inverse functions. So to identify if a function is one-to-one, then that means that one x corresponds to one y and one y corresponds to one x. So to figure this out, we're going to use the horizontal line test. That states the inverse of a function is a function if and only if every horizontal line intersects the graph of the original function at no more than one point. So again, we have to be looking at the original function. So this one right here, this first one, passes the vertical line test, so it is a function. And it also passes the horizontal line test, so we can say that it's one-to-one. Now, this one on the right, it is a function. However, when I go to cross my pencil through it, it intersects at two places, meaning it does not pass the horizontal line test. So that means it does not have an inverse that's a function, not one-to-one. So yes, these both pass the vertical line test, but that's it. They both don't pass the horizontal line test. So looking below, we have some examples. So let's first go around and see if it passes the vertical line test. So the first one does pass the vertical line test. So does the second one. However, this one does not. Down at the bottom, it passes. Over here, it passes. And this last one, it does not. So now let's look at the horizontal line test. The first one does not pass the horizontal line test. The second one does. This third one does. Down at the bottom, it does. This one in the middle does not, and this one does. So if we went back and identified if they were one-to-one or not, the first one is no. The second one is yes. So they both have a check mark, so it's one-to-one. The third one, no. This one down at the bottom, yes. The one in the middle, no. And this last one is also a no, not one-to-one. Okay, so inverse functions when given ordered pairs. So if we have the ordered pair x comma y, then the inverse is all of those x comma y points, but instead we change them into y comma x. So if we're swapping the places of x and y, that means it affects the domain and range as well. So the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. So let's first answer the domain and the range of this original function f of x. So the domain are all the x values. So we have 2, 6, put them in order, 2, 5, 6, 10, with curly brackets that represent set notation. And then the range is going to be 3, 4, 8, and 9. So now what I'm going to do is go back and find the range first, or excuse me, the inverse. So the inverse, like it's set up here, I'm going to switch the x and y places. So my first coordinate point is 3, 2. My second is 8, 6. Third, 9, 5. And then my last one is 4, 10. So if I looked at it like this, and I identified the domain of the inverse, I'm going to have 3, 4, 8, and 9. And if you notice, that's the range of the original. And the range of the inverse is 2, 5, 6, and 10. And if you notice, it's the domain of the original. So keep in mind that f to the negative 1 of x, that represents the inverse. So it's a notation. You don't do anything like exponent properties with it, so it does not mean 1 over f of x. It's just a notation that represents the inverse. Okay, so now we're going to talk about finding inverse functions algebraically, so given the equation. The first thing that you're going to do is use y instead of f of x. So we're going to write in terms of y. Then we're going to switch the places of x and y, solve for y, and then go back and put our notation that represents inverse functions, which is f to the negative 1 of x. So looking at number 1, the first step, change f of x into y. Second step, switch x and y. So it's going to be an x equals now root of 2 minus y. And now we're going to solve for y. So to undo the radical, I'm going to square both sides, which gives me x squared equals 2 minus y. I'm going to subtract 2 to both sides to get x squared minus 2 equals to negative y, and then everything needs to be divided by negative 1. Okay, so we'll have y equals negative x squared plus 2. And then I'm going to change, my last step is to put back our function notation. So we have f to the negative 1 of x equals negative x squared plus 2. Okay, in number 2, same thing. I'm going to change g of x into y. And then y becomes f of x. Oh, I'm sorry. No, that's wrong. We're going to do that at the end. So our next step then is to switch the places of x and y. So we have x equals 2y plus 3 divided by 5. My first step is going to be to multiply both sides by 5. And that will give me 5x is equal to 2y plus 3. To get y by itself, I'm going to subtract 3 from both sides and get 5x minus 3 equal to 2y, and then divide everything by 2. So we get y equals 5 over 2x minus 3 over 2. And then I'm going to rewrite y in terms of the inverse notation. And another way that we can represent this is doing just one denominator, but notice that your fraction bar has to be, this should be 2. Your fraction bar has to go under the whole thing. So try 3 and 4 on your own and see if you get what I get. So for number 3, I got the inverse function of m. Oh, I should make that an m. Is the cube root of x plus 1. And then for number 4, I got the inverse of n equals the quantity 5x minus 4 cubed. Okay, so to see if two functions are inverse of one another, we need to use composition. So we need to put each function into the other function, and we have to do it both ways. So if we do that, what we should get out is x, just x. Not negative x, not x plus 1, none of that, just x. So this first one is going to be, we'll do f of g of x, which is equal to, so g is going to go inside of f. So I'll have the square root of g, and then the rest of f right there. So the first thing I notice is that these 2's cancel, and I have the square root of x squared, which gives me x. So that's good, that's what we want. So then if I did it the other way, and I did g of f of x, I'm going to put the function g into f, which would look like, let's see, f squared minus 2. So the squared and the root sign cancel out, and you're left with x plus 2 minus 2, which gives you x. So again, these are inverses of one another. So if I did the domain of just f, that would be 2 to infinity, because anything less than 2 will give you a negative. I'm sorry, this should be negative 2, anything less than that. which means that that's also the range of my quadratic, and since my quadratic shifts down too, that matches up. Okay, and then the range of my radical, my f of x, is going to be 0 to infinity. So this means that the domain of g, if I just switch it like this, is also going to be the same thing. Now you need to note, this is a domain restriction because g of x is a quadratic, and we're used to all quadratics having a domain of all real numbers. So for these to have opposite domain ranges, then we need to apply a restriction right here, okay? Because if I were to graph my inverse of a quadratic, it would look like this, which would mean it would fail the vertical line test. So because of that, we need to restrict it so that it's only a sliver of it which passes the vertical line test. So go ahead for number 2 and do the compositions of m and n. Remember to do both ways, and then state your domain and range of m and n, and see if you get opposites, so therefore inverses of one another. See if their domain and ranges switch. So this is what I got for the composition m of n, which is exactly what we wanted, x. And when we do the other composition, n of m, we also get x. So that means that they are inverses of one another. The domain of m is all real numbers, negative infinity to positive infinity, and so is the domain. And then looking at its inverse n, the domain and range are also negative infinity to positive infinity. And the last part is graphing these inverses. So what I'm going to do first is highlight the 3 points. And I think mine's off my paper here. Or no, it's like right here. Yep, perfect. So this point down here is -5, -6. So I'm going to plot the point for the inverse, -6, 5, which is right down there. This point up here is -2, 3. So the inverse, because x and y places switch, is going to be 3, -2. And our last point is 4, 6, and its inverse is going to be 6, 4. So then I'm going to do my best with straight lines here. There we go. And all inverses are reflected over the y equals x line. So if my lines were straight, it would look even better, but these are inverses of one another. This last one is going to be done the same way. I'm going to embellish 3 points and switch their x and y places. And this is what I get. I have -3, -2 for this first one, so I'm going to do -2, -3. Up here in the middle we have 0, 1, so I'm going to do 1, 0. And this last one over here is 6, 5, so I'm going to do 5, 6, which is right here. Round this part out, straight line, and again it's reflected over the y equals x line, which all inverses are.